The topic this week is friction. You've known friction since you learned physics taught in high school. Let's brush up on this notion of friction in order to have a chance to solve the problems of equilibrium of bodies, structures, machines, mechanisms with friction present when contacting surfaces that are not smooth. It may be necessary to displace loads, which has led to the transportation means to appear. A simple example of such means is illustrated on this photograph. It is drag. When moving loads with the use of such drag, which could be necessary to do in winter as well as in summer, considerable force of friction occurs, as the sleigh's runners are in contact with the ground or snow. Means of transportation keep being developed into something more advanced, yet the laws of physics which underlie the technologies of moving loads remain the same. In this case, we have a motor sledge as an example. Some other examples of the use of friction in technology are illustrated in the drawings and in this photograph. This is a so-called monkey, an instrument to be used for load being held with the use of the forces of friction and the points of contact of a body with the instrument. Monton's and Coulomb's laws of friction underlie the process of solving equilibrium problems with the presence of friction. The first law states that the force of friction in equilibrium is changing from zero to a maximal value. Then, it is further stated that the maximal force of friction is proportional to the normal reaction and does not depend on the square of the contacting surfaces. The coefficient of proportionality is a so-called coefficient of sliding friction. The coefficient of sliding friction depends on the material of the contacting surfaces and on their condition. The surface may be either oiled or not oiled. An example: polished wood or snow powder. These possess a minimal friction coefficient. This kind of friction occurs when we ski. Rubber against dry concrete, the friction coefficient amounts to 0.6 to 0.85. If we take rubber in contact with a wet asphalt road, we will have a considerably smaller friction coefficient. It should be noted that the coefficient of friction depends not only on the condition of the surfaces, but also on the pressure in the tires. Let's introduce a notion of the friction cone. The cone of friction is a surface which, if formed with a maximum reaction, and the maximum reaction is a resultant obtained as the sum of the maximal force of friction and the normal reaction. It can easily be noted that the tangent of the angle phi of the friction cone is equal to the ratio of the maximal force of friction to the normal reaction and is equal to the coefficient of friction. So, the tangent of the friction angle is equal to the coefficient of friction. If we try and displace the body applying a force which lies inside the friction cone, this body, being in equilibrium under the action of two forces, the active force and the reaction of constraint remains at rest as long as this reaction remains within the friction cone. That is, no force lying inside the friction cone can displace a body over a given surface. It is this statement that explains the principle of action of a monkey instrument. Considering the free body diagram composed for a lifted load, we can see that this load is in equilibrium under the action of three coplanar forces intersecting at one point, according to the three-force theorem. Therefore, whatever the weight of the load, the reaction lies inside the friction cone. This load would not slide out of the monkey claw and will remain in equilibrium.